Okay, so hello everyone and happy Monday to everyone and welcome to our Econ seminar today. First, I would like to say that we will be using Slido as the application to ask questions and participate. So if you scroll down in the webpage that you are right now, so you can see the Slido application. Something nice about the Slido is that you can ask questions at any time during the presentation. And questions will be taken at the end of the presentation, or probably so if John can see them before the presentation, he can take them over. So now it is my great pleasure to introduce John Cassano today. John did his undergrad in Earth Science at Montana State University. Then he got his master's in atmospherics and oceanic science at the University of Wisconsin. Then he received his PhD in atmospheric science at the University of Wyoming. And then he did a postdoc at Ohio State University. Currently, John is a professor at the Department of Atmospheric and Oceanic Sciences, ATOC, at CU Boulder. He's also a fellow of the Cooperative Institute for Research in Environmental Sciences, series at CU Boulder. And he's a lead scientist at the National Snow and Ice Data Center at CU Boulder as well. He has taken part or led 14 Antarctica and 1 Arctic field campaigns, most recently from January to April 2020 as part of the MOSAiC expedition in Central Arctic. With that, thanks, John, and you can take over.
Great, thank you. And thanks for the invitation to talk to you today. So for today's talk, I want to talk about work that I've done with my group over the last decade or so, using autonomous observing systems to study the polar atmospheric boundary layer. And this image that I have on the title slide really captures the 2 different types of autonomous observing systems that we've been using. So in the foreground, you see this remote-controlled aircraft, a drone that we've fitted with an autopilot and instruments to make measurements of the atmosphere. And then in the background, you see a 30-meter tall automatic weather station. And I'll talk about what we're doing with both of these types of observing systems to study the polar atmospheric boundary layer. And so I'll start the seminar today with just a quick introduction to the atmospheric boundary layer to make sure we're all on the same page. And then I'll talk a little bit about work we've done with automatic weather stations in the Antarctic. And then I'll shift and talk about work we've done with unmanned aircraft, drones, and 3 different campaigns that we've done using drones. And then I'll talk about what our next steps are, what we're planning to do moving forward. So the atmospheric boundary layer is, can be anywhere from just the lowest several meters of the atmosphere under light wind, very stable conditions, to a kilometer or more if you have strong surface heating. It's the part of the atmosphere that's directly interacting with the underlying surface, and that's part of what makes it interesting for us. And it's also the turbulent part of the atmosphere. So why would we care about the boundary layer? Why would we study it? First, it's where we live, so it shapes our experience and our perception of what the weather in the atmosphere is. The fact that we expect that temperatures go up and down every day is a function of us living in the boundary layer. If we lived outside of the boundary layer, up in the free atmosphere, we wouldn't see that diurnal change of temperatures with cold temperatures in the morning and warm temperatures in the afternoon. When we step outside and we feel the gustiness of the wind, that's a reflection of the turbulence in the atmospheric boundary layer. And we take that for granted that that's just a feature of the atmosphere, that the wind is gusty. But if we were in the laminar free atmosphere above the boundary layer, we wouldn't experience that. And then things like air pollution and the way it disperses really is controlled by boundary layer features. But scientifically, the reason that my group cares about the boundary layer is that it's the part of the atmosphere that's interacting with the underlying surface, whether that's land or ice or ocean. And so as we think about coupled climate system processes, the boundary layer is really a critical part of this because it's the part of the system where the atmosphere is interacting with whatever the underlying surface may be. So with that, I'll switch and talk about what we're doing to study the polar boundary layer. And so when I got my master's degree at the University of Wisconsin back in the middle 1990s, I worked on a project there maintaining automatic weather stations across the Antarctic continent. The University of Wisconsin has maintained automatic weather stations on the continent since the beginning of the 1980s. This map shows locations of all of the automatic weather stations across the Antarctic continent. The triangle symbols are all ones that are managed in some way by the University of Wisconsin. And I've collaborated with them for more than a decade, most recently working on this project. And the one weather station that I'll talk about today is one that's located here on the Ross Ice Shelf, just southeast of McMurdo Station. And that's this Alexander Tall Tower site. For those of you that are not familiar with Antarctica, so Ross Island is right here. It's on the coast of the continent. It's right at the edge of the Ross Ice Shelf. It's due south of New Zealand, and it's the location of the main US National Science Foundation base on the continent, McMurdo Station. So that's where I've gone through for all of my Antarctic projects. And the standard weather stations that we install and maintain across the continent look like this. It's a 3 or 4 meter tall tower. It has sensors on the top to measure temperature and humidity. Oftentimes it'll measure temperature at least, and possibly humidity at a second level. There'll be a wind vane that measures wind speed and direction. There's an electronics enclosure that has the computer that logs the data. There's a communication system there that allows the weather station to transmit data either by radio or via satellite. And then there's a pressure sensor in here that logs pressure data. And then some of the stations also have an acoustic depth gauge to tell you the distance to the underlying snow surface. And of course, these sites only get visited every couple of years, and so snow will accumulate. And so this information on snow depth is useful. But starting around 2011, we started installing taller automatic weather stations. And the first one that we installed was a 30-meter tower. It was located 160 kilometers south of the eastern tip of Ross Island, so a bit more than 160 kilometers from McMurdo Station. It's on the Ross Ice Shelf, which is floating permanent ice. It's an area about the size of France, and it's a flat surface, so it's actually a ideal place to study the boundary layer because you don't have any complicating effects of topography. And the tower makes measurements of all the same atmospheric properties that our regular weather stations do. It measures temperature, humidity, wind speed, wind direction, and pressure, but does so at a bunch of levels. And you can see the wind vanes at all these different heights on this 30-meter tower. And this tower has been operating continuously since 2011. It records data every 10 minutes. And we use it to study the lowest part of the Antarctic boundary layer. And in some instances in the winter, it extends through the full depth of the Antarctic boundary layer when the winds are weak. So what I want to show today is just an example of why we would use a tower like this and what types of information we can get out of it. And so the results I'm going to show just are based on the first 2 years of data that we collected with this tower. We had more than 100,000 10-minute observations. And what we did with these observations is we fed them into a artificial neural network algorithm called self-organizing map. And what this algorithm does is it identifies patterns in the data. The data that we presented to it were the temperature profiles from this tower. So we had temperature measurements from the surface up to 30 meters. And then, of course, those temperature profiles vary in shape over the 2 years of data that we have over the 100,000 observations that we have. And this self-organizing map, or SOM algorithm, then identifies patterns that span the range of all of the different profile shapes that were observed. And so it's a way for us to reduce the volume of data that we're looking at while still retaining important information about the variability that's present. And we used then the output from this technique, which is also called just a SOM, the result from it. And we use this to evaluate forecast model performance. The Antarctic Mesoscale Prediction System is an operational forecasting model that's run out of NCAR that's used to forecast the weather in Antarctica. And so we use the data from our tower, the self-organizing map algorithm, and the output from AMPS to evaluate the model. So I'll show you a bit about that. And so this first figure that I'm showing is the different temperature profile patterns that this self-organizing map, or SOM, identified out of the 100,000 samples that we put to it. And so each one of these panels is showing potential temperature anomaly over the depth of the tower. So the vertical scale in each panel goes from 0 to 30 meters. And then the horizontal scale is a potential temperature anomaly, and it goes from -6 to +6 Kelvin. And so what you see when you look at all of these patterns, and they're organized by the algorithm, is that the patterns on the right are well mixed. Potential temperature is constant with height, and there's very slight differences at the very bottom of these patterns that are physically important. But then as we move from right to left across this self-organizing map, we see that the stability is increasing, and that the stability is also increasing as we move from the top to the bottom. So the most stable pattern is this bottom left one, and then the most well mixed with just a slightly unstable feature right at the surface is the top right. So once we've reduced the volume of data that we have to this span of patterns that represents all of the 100,000 samples that we had collected, we can do lots of other things with this. And the first thing that we will usually do is match each one of our 100,000 samples to one of these patterns, and then calculate how often each pattern occurs. And so that's what I'm showing here. So the percentages just tell you how frequently each pattern occurs. And then I have the SOM as a smaller figure here just to remind you. But what we saw is that the rightmost patterns are the most frequently occurring ones. These are the ones that have nearly constant potential temperature with height. And this result was surprising to us, because when you read anything about the Antarctic boundary layer, one of the defining characteristics of the Antarctic boundary layer is that it's often stably stratified, that there's an inversion present. And so we expected, when we had this multi-year data set, that we would see a lot of inversion conditions and not these well-mixed conditions that actually are what's observed. And it turns out that this site is a relatively windy site. It's located in the path of what's called the Ross Ice Shelf Airstream. And these strong winds generate enough mechanical mixing to overcome the tendency to generate an inversion in the Antarctic. So the first interesting result for us was just the large frequency of well-mixed conditions. And then you can see, there's several percent of all these different stability types. But this bottom left pattern occurs about 3.5% of the time. This is a very strong inversion. So the strength of the inversion over the depth of the tower is about 12 Kelvin in this pattern. So that's a very strong stability. The next thing that we did is we said, all right, we'll take 2 years of forecasts from the Antarctic Mesoscale Prediction System, the same 2 years. We'll take the same time samples that we have observations for, and we'll calculate the frequency with which AMPS predicts all of these different temperature profile patterns. And what you can see if I flip back and forth is that the frequencies are very different. AMPS largely underestimates the frequency of the well-mixed conditions, and instead forecasts much more of these moderate stability, moderate inversion conditions. And so this is giving us useful information about the physical behavior that AMPS is representing. And it tells us that, aside from any biases that we might calculate, just looking at surface temperature or things like that, it's giving us information about what types of boundary layer regimes or surface layer regimes the model is simulating compared to what's observed. And then our next question, seeing these results, is why is the model behaving this way? Why isn't it reproducing what we see in reality? And so one of the other things that we can do with the self-organizing map is that we can look at other variables, other properties for a given pattern in the self-organizing map, for a given temperature profile. And so what I've shown here, the top left, this is a difference between the strength of the potential temperature gradient across the tower in amps compared to what was observed by the 30-meter tower. And the reds here indicate that amps is forecasting greater stability, a larger potential temperature increase over the tower. And then the blues indicate that amps is forecasting a weaker potential temperature change increase over the depth of the tower. And then the figure on the bottom right is showing the difference between the model forecast wind speeds and the wind speed observed by the tower. And here, blue indicates that amps is forecasting weaker winds than are observed, and red indicates that the model is forecasting stronger winds than observed. And so putting these two pieces of information together gives us a lot of information about why the model is failing to reproduce what is observed by the tower. So if we look on the right side of the SOM, we see in general that amps is forecasting wind speeds that are weaker than observed. And then if we move to the top right, we see that over those same patterns, amps is also forecasting greater static stability. And these two things, of course, go hand in hand. With weaker winds, you have less mixing, and in an environment that's dominated by a negative radiation budget for most of the year, you would expect that that weaker mixing should result in enhanced static stability. And so that's exactly what we see. And so now this analysis is giving us insight into why the model is failing to reproduce the observations. The opposite side, on the left side of the SOM, we see that the model is forecasting winds that are too strong, and at the same time, it's forecasting overly weak stability. And so this is just the opposite side of what I just said. If the model is forecasting overly strong winds, it will generate too much mechanical mixing, and that will weaken the stability in this negative radiation environment. And then the interesting part is in the middle of the SOM, where AMPS is forecasting overly strong winds, but is also generally forecasting too strong a stability. And so then the explanation I've just offered doesn't make sense. And what it suggests is that there are other problems, physical problems in the model. And the most likely culprit here would be the radiation budget at the surface, that AMPS is not generating as negative of a radiation budget as is actually observed. And unfortunately, because this is an unmanned site, we don't have the radiation observations to evaluate that. So that's simply a hypothesis that we have. But by combining the ability of the SOM to distill our data into distinct physical patterns, and then applying or calculating other variables to go along with those patterns, like wind speed, we can start to infer why the model does or doesn't reproduce what's observed. And so it gives us a very powerful way to interrogate the model and to diagnose where the model is failing in what's a very difficult situation for the model to simulate well. The ability to represent the stable boundary layer is a long-standing problem in numerical modeling. And so this gives us some insight into why the model is failing, and gives us a path to think about how we might try to resolve those problems. So I'll now change from talking about work that we've done with the automatic weather stations, and now talk a bit about work that we've done with unmanned aircraft, with drones. And we've had a couple of different campaigns that we've led in the Antarctic. The first one I want to talk about is the first one that we did. So we had 2 field campaigns in September of 2009 and September of 2012, where we went to McMurdo Station on Ross Island, and then we flew Aerosonde unmanned aircraft from McMurdo Station up through McMurdo Sound, the western Ross Sea, to a location called Terra Nova Bay. These unmanned aircraft flights were the first scientific drone flights done by the U.S. Antarctic program. And these were done at the end of the Antarctic winter. And we did that not because we wanted the extra challenge of working during the winter conditions, but because there are no other flights that take place in Antarctica then. So there are a couple of flights that come to Antarctica at the end of August, and then there are no more manned flights on the continent until early October. And so we had, an entire continent's worth of airspace where we didn't have to worry about any conflict with our drone. And so that made logistics of operating much easier. But we also went during the end of the Antarctic winter because this is the most meteorologically interesting time for us to study Terra Nova Bay. And the reason we went to Terra Nova Bay is a combination of three things. So Terra Nova Bay is a location on the coast of the continent that has a recurring POLYNYA, and I'll explain what that is in a minute. It's also an area that gets very strong katabatic winds that drain off of the continent. And then the combination of those two leads to very strong interaction between the atmosphere and the ocean, and causes Terra Nova Bay to be a source region for Antarctic bottom water, which is among the densest water in the world ocean. Our observations with the Aerosonde in 2009 and 2012 were the first and only in situ wintertime observations made over Terra Nova Bay up until that time, and not until research crews called Pipers with the Palmer research vessel from April to June of 2017. That was then the next set of in situ observations that were made in Terra Nova Bay during the winter months. So to start with, I want to explain a little bit about why we went to Terra Nova Bay. So in this schematic, the Antarctic continent is on the right side of this figure, and this blue arrow represents the katabatic winds that drain off of the continent. So katabatic winds occur when cold air that forms over the ice sheet of the continent accelerates downslope under the influence of gravity. It's negatively buoyant, and it will accelerate down the slopes of the Antarctic ice sheet and down to the coast. And then the topography of the underlying ice sheet will channel this cold katabatic flow into just a few places around the continent where most of the cold air drains off. And Terra Nova Bay is one of those places where the katabatic winds converge upstream of the coast. And the end result is that Terra Nova Bay is one of the windiest places on the planet and on the continent. During the winter, it experiences hurricane force winds every month of the year. Its monthly mean wind speeds are of the order of 20 or 25 meters per second. So it's a very windy location. And that wind is important for how the atmosphere is interacting with the ocean, because these strong offshore katabatic winds will push the sea ice away from the coast. And that's what's shown here, is that we have sea ice that's being pushed away from the coast. It's exposing the underlying ocean. And of course, this ocean in the winter is already at the freezing point of seawater. It's, the temperatures are, minus 20 or minus 30 degrees Celsius in the air. And so we have this very cold water that's now exposed to even colder continental air that's draining off of the continent. And so when we get this very cold, dry continental air blowing over the open seawater, we get large upward sensible and latent heat fluxes that extract energy from the ocean. Because the ocean water is already at the freezing point, extracting energy from it leads to the formation of new sea ice. And that's what we see here with these little white dots, the frazzle ice that's forming. And of course, as sea ice forms in the ocean, the freshwater part of the water freezes and the salt is rejected and creates this very cold and salty water that has a very high density. And this very dense water that's forming as new sea ice forms in this POLYNYA, this area of open water, then sinks to the shelf and then sinks into the deep ocean basin to form this Antarctic bottom water. And so we have this interplay between the atmospheric dynamics that drive katabatic winds with this cold air draining off, the advection of sea ice away from the coast, and then the extraction of energy from the ocean by these cold winds that forms new sea ice and creates the formation of this very cold, dense Antarctic bottom water. So we flew our unmanned aircraft up to Terra Nova Bay to make observations of this, to quantify the exchange that was taking place between the ocean and the POLYNYA and the overlying atmosphere. And the tool we used for this was this Aerosonde unmanned aircraft, and here is a picture of one. So they're relatively large unmanned aircraft, or bigger than the ones that we've used since then. It gets launched off the back of a pickup truck, so it's mounted in a little rack here. This pickup truck will accelerate up to about 50 miles an hour. When it gets going that fast, the Aerosonde lifts out of its rack and takes off, and then continues flying the scientific mission. And so The Aerosonde, it's about a 3.5-meter wingspan. It weighs about 20 kilograms. Important for us is that the endurance is up to 19 hours with the way that we had configured them, and we could do missions that flew 1,000+ kilometers. When the plane was flying, we could be in contact with it via radio when it was close to where we were operating, or by Iridium satellite phone when it was further away. And so we always were in contact with the aircraft. We could see the conditions it was measuring. But the plane largely flew in an autonomous mode, but we could change its flight plan during the flight to sample features of interest as we came across them. And we outfitted the Aerosonde to measure atmospheric state. So we had measurements of wind speed and direction, humidity, temperature, and pressure. We had infrared, downward infrared looking thermometers to measure the temperature of the surface we were flying over. We carried a camera to take images of the surface when we had daylight. But here we'll talk about the atmospheric state primarily. And first I want to show you what it looks like to fly or to launch one of these Aerosondes. And so to orient you, we're in Antarctica, we're on a runway that's used for manned aircraft during the main summer season. The pickup truck here has an Aerosonde mounted on the top of it. There's a van parked here with someone standing outside. This is a pilot. He's going to fly the plane with a remote control manually when it first takes off. Once he's happy that the Aerosonde is behaving correctly, he puts it into autopilot mode and then it flies away. And so what you're going to see is this truck is going to accelerate towards us to about 50 or 60 miles an hour on this ice runway. The Aerosonde is going to take off and then fly off up to the north to Terra Bay. And then most of our missions were of the order of about 15 or 16 hours. Because this was at the end of the Antarctic winter, we only had a few hours of daylight each day. So we had to time our flights to take off when we had daylight so we could see what we were doing, and time them so that we also had daylight when the planes came back. So the pilot that was flying it with remote control could see what he was doing to land the planes. And so over the 2 seasons we went down in 2009 and 2012, we did a total of 30 flights with about 300 flight hours. And so we were quite happy with the success we had of flying these aircraft in what was a very physically demanding environment. We flew in temperatures down below -40°C. We flew in winds exceeding hurricane force. And then we did these very long missions during the polar night. So a very challenging environment to work in. And we were really happy with what we were able to do with these Aerosondes. And then just to show you the end of a mission. So here we'll see the plane landing. This little white dot is the plane, and it's being controlled by the pilot that has a remote control. And so you're going to see as the plane's going to circle and then land on the runway. And so it's just making its final approach. It's turning to come parallel to the runway now. And now it's lined up for that final approach. And I'll add that, all of this is being done while the temperature was about -30°C. And so, a very challenging environment for the pilot to be working with very fine motor control to fly that plane with a remote control in those cold temperatures. So I'll show you a few samples of the types of data that we collected. And the first thing I'll do is show you a combination. So the bottom left in each of these next slides is going to be a visible satellite image of Terra Bay. And to orient you, the coastline is sort of running right through roughly the middle of this picture. Everything to the left of this is Antarctic continent. and there are a couple of glacial valleys here, and everything's covered by permanent ice. Everything to the right is the Ross Sea in Terra Nova Bay, and it's covered mostly by sea ice. So everything looks white. And the only exception is this little bit of dark right at the coast. This is where the katabatic winds are starting to push the sea ice away and opening up a POLYNYA. And then the top image are the winds that were measured during one of our flights. This one was on the 18th of September. The color scale here is showing speeds in meters per second. These oranges are about 30 meter per second winds. And what I'll point out is that this katabatic flow coming off the continent is a very narrow jet of strong winds. So we have winds that are just, a handful of meters per second at the southern and northern edge of Terra Nova Bay, but then these 30 meter per second winds right down the middle of the bay, and this is of the order of, tens of kilometers across. So it's a very narrow jet of strong winds. The next day we flew up again. We had a second mission. The wind speeds now are in excess of 35 meters per second. Again, you see that the winds drop off to basically zero at the north and south ends of Terra Nova Bay. And in the satellite image, you can see that this area of open water is expanding, that area of dark. And you can see some thin clouds covering the area as well. And then a few days later, the winds are still blowing at almost 35 meters per second. The POLYNYA has now opened up quite a bit. There's a lot of open water, but you see also a lot of this new sea ice that's forming, and it's aligned with the wind direction. So we get these streamers of ice that form on top of the ocean. And then another couple of days later, the winds are finally starting to die down. They're, of the order of about 20 meters per second over much of the bay, but still a little core of fast winds right at the coast. And you can again see this large area of open water and loose sea ice that's formed as a result of this katabatic event with winds up to hurricane force. So this gives us a really detailed picture of what the wind field looks like. It's a useful way for us to visualize what's happening. And prior to these flights, we never really had any direct measurements to see what this wind field looks like. High resolution modeling work, suggested that the wind field looked like this, but we didn't ever have any actual observations to confirm that. And then a couple more things to look at. So here I've plotted temperature and dew point temperature and wind speed as a function of distance flying away from the coast. So I've highlighted in this little inset in the bottom left. So we had an aircraft that flew parallel to the coast. It found where the strongest winds were, and then it circled around and it flew parallel to those strong winds downstream over the POLYNYA. And you can see on this day, the POLYNYA was relatively open as a result of the previous days of strong winds. And so what we see is that near the coast on the left side of this image, the temperature of the air coming off the continent is cold. It was around minus 21 degrees Celsius. And as we flew the 40-ish kilometers downstream over the POLYNYA, you see this gradual warming. This is a reflection of the ocean transferring heat to the atmosphere, that sensible heat flux up from the ocean. In red, we have the dew point temperature, and we again see this increasing dew point temperature reflecting the evaporation from the open water into this cold, dry air that's blowing over it. And then finally, the black dots are showing the wind speed, and that's on the scale on the right. And so at the coast, we had wind speeds of about 20 meters per second, and they decreased down to something like 13 or 14 meters per second over this 40-kilometer distance. And so this image is really encapsulating what it is we wanted to measure. We wanted to see how the atmosphere was interacting with the underlying surface. And so we see the warming, we see the moistening, but we also see the momentum loss from the atmosphere to the underlying surface. That's important for generating waves, for providing the mechanical force to move sea ice away from the coast. And so this gives us a very detailed picture of how the atmosphere is interacting with the underlying ocean, where we previously didn't have any data to see what this looked like. And then, not only did we fly the aircraft at these constant heights over the ocean to measure the downwind changes, but we also would have the aircraft do profiles that would allow us to look over, the lowest kilometer and a half of the atmosphere. And so here I've plotted 4 profiles that we took on the same day as that previous slide. The blue profile is right at the coast, and then going to green and orange and red. Each of these profiles is about 10 kilometers further downstream. And so what you see is that we have this downstream warming. The boundary layer top is, starts out at about 200 meters, right where this inversion starts, and deepens as we move downstream. And this is all consistent with this large upward heat flux that we expect from the open water as this cold air blows over it. But by having these profiles, we can actually estimate how much heat is being put into the atmosphere. And on this day, we estimated an upward heat flux of about 580 watts per meter squared is required to give us this change in atmospheric state. We did the same thing with humidity, and we also used wind profiles. So here we have wind speed profiles. The blue again is at the coast, and then green, orange, and red is moving further away from the coast. And from these wind speed profiles, we could calculate the forcing for the flow. So from the changes in wind speed, we could estimate the acceleration that these air parcels were experiencing as they moved downstream. We had pressure measurements on the aircraft, so we could estimate the along wind pressure gradient force. And then from the wind measurements, we could calculate the Coriolis force and derive the turbulent drag, the friction that was occurring. And so we could provide a very quantitative evaluation of exactly how the atmosphere was interacting with the underlying surface, both in terms of heat and moisture fluxes, but also in terms of the momentum flux. So this gives us a very detailed data set for understanding the coupling between the atmosphere and the underlying surface. And then I'll end this discussion of Terra Nova Bay with a couple of photographs. This is one over the largely open water portion of the POLYNYA. In this picture, the wind is blowing from the top left to the bottom right. These white bands are bits of new sea ice that are forming that are aligned with the winds. And in fact, you can see here white caps on tops of these waves in this 25 meter per second wind environment. And then if we go further downstream, here we see that frazzle ice has formed into pancake ice. So these are thin plates of ice, a meter or two across. But in this picture, you can also see this wave pattern generated by the strong momentum transfer to the open water that creates these large waves. And we estimated wave heights, of the orders of 10 to 20 meters forming in Terra Nova Bay in response to these strong winds over this 30 or 40 kilometer fetch of open water. And that those waves propagated into where we had almost continuous sea ice cover. And in fact, even when the pancakes had consolidated into a thick sheet of ice, we could still see evidence of the waves propagating through that ice pack. But the Aerosondes, for all of their capabilities, required a lot of effort to operate. We brought a team of 4 engineers and pilots with us from Aerosonde, the company itself, to do all of the flying and maintain the aircraft for us. We needed a runway that we could drive a pickup truck at 50 miles an hour, and they were very expensive to operate. And so after that, we started doing unmanned aircraft flights with basically hobby remote control planes that we fitted with autopilot and instruments. And we found that these were a very useful way for us to observe the Antarctic boundary layer as well. And so the first of these small unmanned aircraft that we use is called a SUMO. SUMO stands for Small Unmanned Meteorological Observer. It was developed by some remote control hobbyists in Germany in collaboration with scientists from the University of Bergen. And these have been used by a number of groups around the world. We took them to Antarctica. We've done 6 campaigns with them between January of 2012 and June of 2017. And so the 2 maps, the first map on the left is showing the Ross Island area. So this is due south of New Zealand. McMurdo Station is this red dot right on the tip of Ross Island. There are a couple of runways that the U.S. program operates, Williams Field and Pegasus Runway. We did a lot of flights with our unmanned aircraft just right there. This red dot up on the image, but to the south, is the 30-meter tower that we looked at earlier in the talk. We did a campaign out there. And then there's a red dot here in the mountains west of McMurdo Station. This is in the Antarctic, or the McMurdo Dry Valleys. This was a campaign we did in collaboration with the New Zealand Antarctic program. And then the image on the right, the map on the right, is showing the Piper's cruise. This is a research cruise that went into the Western Ross Sea from April to June of 2017. And we did SUMO flights as part of that campaign as well. The SUMO is a very different platform than the Aerosonde. It's small. Its wingspan is only 0.8 meters. It weighs a little bit more than half a kilogram. It's a battery-powered platform. Its endurance is about 30 minutes. You can fly it from the surface to about 4 kilometers before the battery runs out. And we outfitted it to measure atmospheric state temperature, humidity, pressure, and wind. But unlike the Aerosonde, it's very easy to operate. It's a field team of 2 people. One person operates a remote control, so they can manually control the aircraft. And then there's a ground control pilot that operates ground control software for when the plane is flying in autopilot mode. And the way we would operate the SUMO is that we would go out to whatever site we wanted to sample, and we would just fly the aircraft all day long, just do repeat profile flights in the lowest 1,000 meters of the atmosphere to look at how the boundary layer was changing on sub-daily, close to hourly timescales. That gives us a sense of boundary layer behavior that we don't get from the large surface network of observations on the Antarctic continent and the very few twice daily radiosondes that are launched. And so I'll show you what a SUMO flight looks like. So here we are in the McMurdo Dry Valleys. The plane is launched by hand. So one person just throws the plane and then the other person flies it with a remote control. And so you'll see the plane take off, and then at the end of the video, you'll see the plane landing as well. Oh, sorry. And the plane's coming in on the right side here. And just like the Aerosonde, it just belly lands, but it's pretty easy to operate. And then here's a picture of myself with one of my graduate students, Melissa Nigro, out at a field camp out by the 30-meter tower on the Ross Ice Shelf. And so we spent a couple of weeks here flying the SUMOs. And then the ground control software looks like this. You have a map that shows you where the plane is, and it gives you information about what the flight plan is. You get information about how the aircraft is behaving and controls to change what it's doing. And you can also interrogate the sensors on the aircraft to see what it's measuring. And most of the time you are staring up at a tiny little dot that's circling above you. And at 1,000 meters, it really is a small dot, and it's easier to just lay on the ground and look straight up and watch it. So I'll show you a few observations that we made late winter at Pegasus Runway right near McMurdo Station, just to give you a sense of what types of information you get by sampling the boundary layer at these sort of hourly time scales. And so each set of figures that I show you will be the same. It'll be temperature and height over the lowest 600 meters of the atmosphere. The colors just show different times, usually over the span of about 24 hours. And on this 24-hour period, what really struck us, there are 2 things. One is the strength of the near surface temperature inversion. So in the lowest 200 meters, the temperature increased by more than 10 degrees Celsius. We had very cold temperatures at the surface. Most of that inversion was, in the lowest 30 meters of the atmosphere. So a very stable situation. But the other thing that was striking on this sequence of flights is how steady state the atmosphere is. This is something that you just don't see hardly anywhere in the atmosphere, and to see the atmosphere just stay in this persistent state for a 24-hour period was something that was a bit surprising to us and interesting to observe. But most of the time, what we would see over the sequence of flights is that the atmospheric state would change. And in this case, what we saw is that the top of where we're sampling, there was almost no change. And we usually take the top part of this flight to represent sort of the large scale advective changes that are taking place. And so on this sequence of flights, we infer that there is very little advection taking place, but the surface temperatures cooled quite a bit over this time. And so this is a reflection of changes within the boundary layer. And in this case, it was a change from cloudy to clear conditions that allowed the surface radiation budget to go negative. And then the surface responded and developed this strong surface inversion. On this other day, what we see, the temperatures aloft warmed over time. So we infer that we had warm air advection. We had a very strong inversion right near the surface that was decoupling the surface from what was happening aloft. And aloft, in this case, is only 100 meters and up. So real close to the surface, but completely decoupled from the surface. And in fact, with this series of flights, while the warm air advection was taking place aloft, the surface temperatures were cooling off, showing us, how very stratified the atmosphere is in these winter conditions in the polar regions, and how you can have very different behavior over thin layers of the atmosphere. And of course, this is a real challenge for numerical models to represent this very different behavior over such shallow depths of the atmosphere, while also trying to capture the behavior of a very stable boundary layer with what's likely to be intermittent turbulence. And then another example, in this case, we had, again, warm air advection taking place aloft. As this warm air moved in aloft, it generated a very strong shallow inversion, in just the lowest tens of meters of the atmosphere. And then eventually the surface caught up, and in fact, the warming at the surface exceeded what happened aloft as a result of the warm air advection. And so, there's this real rich behavior that's taking place in the atmosphere, and that these hourly timescale observations that we can get with these unmanned aircraft, from basically any environment that you want to go to on the continent, any place that you can put yourself and a couple of people and a little bit of cargo, you can make these measurements. And then the last thing I'll talk about is the field campaign that I took part in just the beginning of this year, from January to April, called the MOSAiC campaign. This took place in the Central Arctic. This photograph is myself and one of my students, Gina Joseph, after one of our unmanned aircraft flights. Here we're flying a different aircraft. It's called a Data Hawk. It's similar to the SUMO, but makes some turbulence measurements as well, which is a nice addition to the sampling that we're getting. This flight took place at about 86 or 87 degrees north, the middle of March, so right at the end of Arctic winter up near the North Pole. And MOSAiC was an international effort. It just ended in October. It was a year-long expedition, went from October last year to October of this year. It was a drifting camp based around the German icebreaker, the Polar Stern. There were 5 science teams. There was atmosphere, ocean, ice, biogeochemistry, and ecosystem. This map on the right, the blue track shows where the icebreaker was frozen into the Arctic ice pack last October, and then it drifted with the sea ice until April, the end of this blue track, and then it sailed out to Svalbard to exchange crew, and then came back and finished its drift out of the ice. Gina and I were on the expedition from about here, almost its most northerly point, until the end of this blue track. And so we used these Data Hawk unmanned aircraft to observe the Arctic boundary layer in the high Arctic at the end of the winter. Very challenging environmental conditions. We flew in temperatures from down to almost minus 40 degrees Celsius to as warm as 0 degrees Celsius. We had a lot of storms in the several months we were on the expedition, with winds up to 25 meters per second. That led to very active ice dynamics. So when we arrived, you'd get out and walk on the sea ice, and you really wouldn't realize that you're on sea ice because it was a continuous ice cover. But once the storm started rolling in, the ice became very dynamic, and we would have lots of leads that were forming that made it difficult to operate. And I'll show you a video of the Data Hawk flying. This is launched off of rails by a bungee cord. And so you'll see us launching the plane.
Right.
I am ready whenever you are.
I'll count you down. 3, 2, 1, go. Did you take it? Right.
And then I'll show you the landing as well. But just like the Aerosonde and the SUMO, it lands on its belly. And so the plane's going to come around from the left and land in front of us. So here it is.
Oh, this is going to be awesome. Woo!
And Gina and I were very excited. This was our first successful flight on MOSAiC. So we were both very happy that the plane performed well. And then just 2 more slides before I conclude. Here, this is just a sample of the different temperature profiles that we observed during our flights. And so you can see very strong inversion conditions. You can see the very cold temperatures we flew in. We had some elevated inversions. We had some convective conditions with when the sun came up and we started to get some surface heating. So we observed a wide range of boundary layer behavior. We observed the seasonal transition from late winter into early spring, and then another team took over for us that continued to make measurements into the summer. We had several cases of strong warm air advection with approaching storms that were real interesting to look at, with very warm temperatures aloft over the cold surface. And then just one case that I'd like to show. The blue dots are the temperature, that's on the bottom scale, and then the red is the wind speed on the top scale. And here we had a very shallow wind mixed dry adiabatic layer, and then a strong inversion sitting on top of that. But what was interesting in this case is that aligned with this inversion was this very pronounced low-level jet. And that's one of the things that we're interested in studying is low-level jets and the impact of the varying turbulence, as we move through these different stability regimes on driving those jets. So the autonomous observations that I've talked about today, we've made over a range of polar conditions. We've collected data year-round with both automatic weather stations and unmanned aircraft, and we've done this over a variety of surfaces. Permanent ice and ice-free locations in the Antarctic, as well as over sea ice and POLYNYA environments. We've observed boundary layers from very strongly stable to deep convective conditions. The tall tower data that we looked at, that SOM analysis allowed us to really understand where the numerical model was failing for different boundary layer regimes. The flights we did over Terra Nova Bay gave us quantitative estimates of the surface coupling between the atmosphere and this POLYNYA environment in this very climatically interesting area that generates Antarctic bottom water. And then the hourly timescale observations we get with the smaller unmanned aircraft, the SUMO and the Datahawk, provide insights into both what's driving the near surface changes in thermodynamic state, both in terms of advection, but also in terms of boundary layer processes. And all of these observations provide a real rigorous test for weather and climate models because they're giving us a perspective on the atmosphere that we don't get from any other observing tools that we have. And so, the hope is that the types of process level analysis that we can do with this data gives us an improved understanding of how the coupled polar climate system is behaving, the interaction between the atmosphere and that underlying surface. It gives us a way to evaluate weather and climate models that we can't do with other observations. It lets us look at mesoscale details like those maps of the winds that I showed in Terra Nova Bay, but also details of how the boundary layer is evolving and what's driving that. And hopefully this eventually leads us to a better representation of these processes happening in the bottom of the atmosphere and the coupling to the overlying or to the underlying surface. Next steps, we're putting up another 30-meter tower in West Antarctica. It was supposed to be put up this year, but COVID had other plans for us. So we're delayed a year. It'll go up late 2021 and be there for at least 3 years. We'll have another unmanned aircraft campaign at that site. And it'll allow us to look at atmosphere ice sheet energy exchange processes in one of the fastest warming locations on the Antarctic ice sheet. And it'll be similar to what we've done with the tall tower on the Ross Ice Shelf. And so with that, I'll end with a picture of the SUMO circling at night over Pegasus runway. So the colors are the wingtip and tail lights on the plane as it circled overhead. And I'll take any questions.
Thanks, John. It was very interesting. And just as a reminder to everyone, if you have questions, please write them on the Slido application. So far, I don't see any question. I think any questions. So I think I can start. So okay. It's very interesting everything I think I have so many things. So for these permanent weather stations, so how often do you need to go and maintain or change them? Or
yeah, so the weather stations, that whole network that I showed you, none of the sites get visited more than once a year, and often the sites aren't visited for several years at a time. We've had the tall tower site, I think, went 2 or 3 years between site visits, and so the group at Wisconsin that helps us install these sites, they've been putting up weather stations in the Antarctic for more than 30 years. And so they have a real good handle on what instruments survive and how to make these stations very robust so that they can go for years at a time without being serviced. Yeah, and of course, we'd love to get to them more often, but the logistics of polar winter conditions when we can't get out to any of these remote sites, and just the logistics of, trying to get flights out to these sites limits how many sites we can visit in any given year.
Yeah.
Okay,
Now we
so
can
I
see
see a couple of questions.
Yep.
So one, so the air-sea exchange over POLYNYA doesn't seem like it'd be resolved in global climate models with 100-kilometer resolution. Do you have a feel for how much air in the surface energy budget this represents in the region? Yeah, so we've done a little bit with looking at this, not with the global climate models, but with previous generation reanalyses, so 50 to 100-kilometer resolution, and they really fail to capture any of the detail of what's happening in the POLYNYA. The scale of that POLYNYA is tens of kilometers, in the north, south, and east, west direction, and so a 50-kilometer model, it's maybe one grid point. And so there are several problems. If you don't have the sea ice represented correctly, then of course you're not going to represent that lack of insulation between the ocean and the cold atmosphere. So that's the first problem that would apply for global climate models as well. The next problem is that the dynamics of the katabatic winds, you need to well resolve the boundary layer and over the Antarctic ice sheet to get that strong inversion that drives them. But you also need to resolve the glacial valleys that channel these winds that accelerate them to such strong wind speeds over Terra Nova Bay. And again, what we've seen with AMPS, which is a relatively high resolution model, captures the wind speeds okay, but things like the reanalyses, at 50 kilometers, don't really come close to getting the right wind speeds, and I would expect the global climate models are similarly failing with that. And so, it's a small area that has these. We've calculated heat fluxes, combined sensible and latent heat fluxes in excess of 1,000 watts per meter squared over the POLYNYA. So that's a big heat flux. It's the opposite sign, and it's 3 orders of magnitude bigger than the fluxes that you would expect to have over the sea ice at that time of year. So it's a small area. So in the regional sense, maybe it's not that important, but it's really critical for changing that ocean column in that small area and allowing the model to generate that deep Antarctic bottom water. So there's another question about if the data is publicly available. Yep. So both the Aerosonde and all of the SUMO data is available on the U.S. Antarctic Program data center, the USAP DC. So if you look for that, you can find links, and then all the data is freely available there. The data we collected during the MOSAiC campaign, we're just finishing processing and quality controlling that. I'd expect within the next 6 months or a year, we'll have that data posted at a public data center as well. And then there's also a question about the metadata and the quality assurance, quality control to the raw data. So most of the quality control we do is manual. So we'll, fly the flights. We'll plot up the data. We'll look at it. Really, there isn't very much in the data that we flag and say there are any issues with it. The biggest issue that we have is sensor lag. So, we'll do these flights where we fly up and down, and you can see slightly different slope of the lapse rate for the up and down, reflecting the sensor lag. It's of the order of several seconds for the temperature, as best we can figure. The humidity measurements, particularly in the winter conditions, are terrible. So those I don't trust at all. But the sensor lag for that, even in the polar summer conditions, is of the order of tens of seconds. So it becomes a little bit difficult to interpret the data. But mostly we've just plotted the data or provided the data. As we collect it, we've pulled out the obviously bad data points, but there are really very few of those. And then we have a couple of data papers that we've written that go along with the data that are referenced on the websites that talk about things like the sensor lag. So then the question about the difference in the quality of the observations and the duration between the Aerosonde, the SUMO, and the Data Hawks. So the duration is very different. The Aerosonde was gas powered. It flew with aviation fuel, had a gas motor, and we could do flights. Our longest flights, I think, were about 19 hours, but most of them were of the order of 15 hours. The SUMO and the Data Hawks, they're battery powered. They use lithium polymer batteries with an electric motor. And the battery endurance and the polar conditions we were flying were between 30 and 40 minutes. When we did our first winter campaigns with the SUMOs, we were a bit concerned about what the battery life would look like when we're flying in -30 or -40 degrees Celsius temperatures. And to be honest, we saw very little reduced performance with those cold conditions. That was a bit surprising to us. As best we can figure, the power draw from the batteries is really large when you're flying, and we think there's a bit of self-heating that goes on. And then in terms of quality, the Aerosonde and the Data Hawks actually both fly with Vaisala radio sonde sensors. So the data quality is exactly the same between them. The SUMO uses a little bit smaller, a little bit cheaper instruments, but we haven't seen anything that made us really question the quality of the measurements. Certainly within a few tenths of a degree Celsius. We did some flights where we flew right next to the 30-meter tower and compared the SUMO measurements and the tower measurements, and they were, like I said, within a few tenths of a degree Celsius of each other. So in general, we've been real happy with the quality of temperature, pressure. Like I said, humidity can be a little bit iffy in the real cold conditions. The sensors are pretty slow. The wind is a derived quantity in all of them. It's based on airspeed measurements with the pitot tube, as well as GPS measurements of the ground speed. There, probably 1 meter per second is about what we think is the reliability of the wind measurements. For places like Terra Nova Bay, where you're flying in 30 meter per second winds, 1 meter per second isn't too bad. Yeah, so we've been happy with both the ability of the aircraft to fly in these harsh conditions, as well as the quality of data that we've gotten from them.
So I have a couple of questions myself.
Sure.
So now that you started going to the Arctic, I guess you have many experience in Antarctic.
Yes.
But now that you started the Arctic, are you planning to go more often or in the future? Or
I don't have anything planned in the near future. The Arctic is, it's a more challenging environment to work in. You're based off of a ship rather than at a field camp or a research base like McMurdo Station. Just the time scale of the trips is longer. I spent 3 months in the Arctic, whereas most of my Antarctic trips are something like a month or a month and a half. So I certainly am happy to go back to the Arctic, but I don't have any immediate plans. My next field campaign is for the Tall Tower in West Antarctica, and that'll be something like a month and a half. I will also say that, being out on the sea ice in the Arctic and having to worry about polar bears added a level of stress that we don't have in Antarctica. So we always had to have someone with a rifle out with us. In fact, the day after I left the MOSAiC campaign, a polar bear came right up to the tent we were using for our drone flights. So it was always on our mind. Also being on the sea ice, with it being very active, we had lots of conditions where leads would open between us and the ship while we were flying. And then you had the challenge of how to safely get across that open water without falling in. So that was a very challenging environment to work in. Okay, so have you tried using drones or considered to program the flight path instead of using remote control? So the remote control we only use that for takeoff and landing. And in fact, all of the platforms that we flew, we could fly fully autonomously from takeoff to landing. We just felt a little bit safer flying the planes manually for takeoff and landing. But all of the research part of the flight was all done autonomously. So we had a autopilot and ground control software that would control how the plane was flying, and we would just tell it, to profile up or down, or to stop what it was doing, or to change its path. But it was all being done automatically. So that was a very good way to fly. I wouldn't want to fly the planes manually for 30 or 40 minutes and -40 degrees Celsius temperatures. I was happy to take my hands off the control and put them in gloves with hand warmers.
Great, thank you.
Mm-hmm.
Thanks, John.
Well, thank you, everyone.
Yeah, thank you. And just as a reminder, so we will make available the recording of this presentation in our YouTube channel.
Okay.
So you can find it there. So, and thanks, John, and thanks everyone for joining.
Yes, thanks, everyone.
See you, everyone. Bye-bye.
Bye-bye.